The Sun slightly larger than Jupiter. But that isn't the right depiction of the scales. The Sun is so massive that you could fit about 1,000 Jupiters inside. Impressive as it is, our Sun isn't the biggest star in the universe or even our galaxy. That title goes to UY Scuti, and compared to it, our star is like a tiny pebble. But there's more. Scientists have stumbled upon something even more mind-boggling. An enigmatic ancient star with a black hole inside. It's an astronomical mystery that both puzzles scientists and can potentially explain how the universe came to be what it is today. But how is it possible for a black hole to exist inside a star? Why were these stars so gigantic? And what would happen if a black hole star wandered into the solar system? Are like cosmic blacksmiths. In their fiery cores, they're forging the majority of the elements we observe in the universe. But the stars that could have existed at the very beginning of the universe were something different. Instead of conventional stellar cores, they harbored black holes within, allowing them to grow to unimaginable sizes and beyond. Ordinary stars arise from the clouds of gas and dust as gravity makes the densest regions of the cloud collapse. The resulting mass of material heats up and creates a protostar, an early stage in the evolution of a star. Eventually, the newly formed hot core accumulates enough matter from the surrounding rotating disk of gas, becoming a main sequence star that starts producing energy through nuclear fusion. It took our Sun about 50 million years to reach this phase. The majority of stars will spend most of their lifespan as main sequence stars, but eventually they will either become white dwarfs if their mass isn't big enough or go supernovae. After a star blows up, it can end up as a black hole or a neutron star, and the path it takes depends on how massive it was. When our Sun runs out of hydrogen in about 5 billion years, it will turn into a red giant, expanding 200 times in size before finally shedding its outer layers and transforming into a white dwarf, a celestial object that's roughly 200,000 times denser than the Earth but about the same size. This dense sphere will slowly cool to about 18 million degrees Fahrenheit, and in about 10 billion years, the white dwarf Sun will crystallize. The process is somewhat similar to how water turns into ice. Although the material is different, in the case of the Sun, it will be carbon and oxygen solidifying. And stars over 10 times the mass of the Sun will have a different fate. They're big enough for their cores to collapse after a supernova, but they lack the mass required to become black holes. So where does this leave them? Deep inside these stars, the extreme pressure squeezes every proton and electron so tightly they merge to form neutrons. Neutrons cannot be compressed any further, so they counter gravitational pressure and the star finds a new balance. Neutron stars are the densest objects in the universe apart from black holes. They can be just the size of a small city, roughly 12 miles, but still have a mass of the Sun. On Earth, neutron star material the size of a sugar cube would weigh as much as 1 billion tons, about as heavy as a mountain. But how do stars become black holes? While the star is still active, the two prevailing forces work against each other: nuclear fusion and the intense gravity created by the star's own mass trying to squish it. Once there's no fuel left to power nuclear fusion, there's no longer a force to counter gravity, and the star collapses on itself, just like the controlled demolition of a concrete building. Einstein believed that anything could become a black hole if it had sufficient mass and was compressed inside a certain radius. Black holes keep on growing throughout their lifespan, devouring any material that gets too close. When this happens, the region where gravitational pull becomes so strong that nothing can escape increases, and the black hole consumes even more nearby material. It's somewhat like the sinking of ground due to the collapse of underground structures. Although with black holes, it's a gravitational sinkhole, gradually accelerating as its event horizon grows. Normally, black holes have a limit on how fast they can expand. This happens because of something called the Eddington luminosity limit. Basically, it's the point at which a black hole can't take in material faster than it already does. If you were filling a car tire with air,